All right, guys, last problem of the day. And what you have is two small discs A, B. A has a mass of 3 kilograms, and this B has a mass of 1.5 kilograms, sliding on horizontal frictional steps again. So you're looking top down, think of it like a billiards table, right? So there's no change in height that's happening. They're connected by a cord, which is 600 millimeters long, and then spun counterclockwise about their mass center at a rate of 10 radians per second. You're told at t equals 0, the coordinates of the point G are 0/2. So basically this y naught bar is equal to 2 meters. You're told the average velocity of the mass center is this vector over here. So 1.2 I hat plus 0.96 J hat. Then you're told shortly thereafter the cord breaks, and then A is observed to move along a path parallel to the y-axis. So A is just moving up, and disk B is moving along a path which intersects the x-axis at a distance of 7.5 meters from O. So right at this point over here, you're asked to find the velocities of A and B after the cord breaks, and the distance A that this horizontal is traveling parallel at to the path of B, right? So this B has reached this B prime location over here. All right, so what we are asked to find is the unknown velocities after these break up, right? So we want to know what is VA, and we know we can write itself in a vector form, right? So that's just equal to VA I hat. So there's this one unknown, right? And then for VB, right, what we can say is that VB has two unknowns because it'll have two unknown components. So VB x I hat plus VB y j hat. The number of unknowns that we have is 1, 2, and 3, right? So because B has two unknowns because we don't know anything about its direction, so it's going to have two components, whereas VA, we are told, is traveling horizontally up. So we need three expressions, guys, and this we're going to get from doing linear momentum in vector form. Remember, when you do an equivalence in vector form, you will get the number of expressions in terms of how many orthogonal directions that you have. So if you're doing this in 2D, you will have I and j hat components, so you're going to get two expressions for from looking at the momentum. So original momentum of the system, so if you look at the linear momentum, right, it's given to us because you know what the velocity is. So you can say that the linear momentum is basically L naught in vector form is just equal to the mass of the system times your velocity vector. Oops, not like that. So it's going to be V bar like that. So it's basically this quantity over here, right? So this is equal to total mass of the system. So it's 3 plus 1.5. So you get 4.5 kilograms times 1.2 I hat plus 0.96 J hat, like that, right? Okay, so this is your initial linear momentum of the system. Then your final linear momentum of the system, not the final, but let's say the momentum that you're going to equilibrate it to, let's just say that that's equal to L, that's going to equal MA times VA I, like that, plus MB times this vector quantity over here, right? So let's just write it out in vector form. So you get MA times VA plus MB times VB, right? So plugging these in here, what you see is you have one expression. Sorry, you'll get two expressions, right? Because you'll be able to compare the y hat and the j hat components. So you'll get 4.5 times 1.2 I hat plus 0.96 j hat, right, is basically equal to whatever your MA is. So that is 3 times VAI plus 1.5 times VB x I hat plus, you know what, getting rid of this bracket, just confuses things. So VB y j hat like that, right? So you have VB x I hat plus VB y j hat. So this expression over here is two expressions, right? And we have three unknowns, but we have two of them written out. If you compare your I hat to your I hat, and if you compare your j hat to your j hat, right? So this here is two equations. All right, then you need one more equation, and that you get from the conservation of energy. All right, so initially you can say that the conservation of energy, for the conservation of energy, so there's no external force, so it's just energy remains conserved. So for conservation, right after spinning, right? So for conservation of energy, we saw today that you can write the expression, and we'll see it for the system, but you can say that that's equal to half times m times whatever the magnitude of V naught is to the squared, right? And that's for your centroidal frame of reference, plus you can say half ma times VA prime squared. Now remember, this is the velocity in the centroidal frame of reference, plus half m VB prime squared like that. And this is just after spinning. And just after spinning, what you're told is that it starts moving at 10 radians per second. Now, the thing to notice is, so this we know, everything we know except VA prime and VB prime, right? So for VA prime and VB prime, what you've got to do is, right, so you have balls that are like that, right? And you have your centroidal that's somewhere there, right? And you know the total length is 0.6. You know that this is 3, this is 1.5, right? So you know that it's moving with a certain angular velocity. When you spin it counterclockwise like that, this will move with the A prime, and we know, you guys know this, that this is going to equal, when you're looking at your frame of reference, which is moving with in the centroidal flame, which is at the center like that. Messing this up big time. But anyways, you have a centroidal frame of reference, and it's in that frame of reference that you're finding the velocity. So this is just going to equal this distance. So it's basically just equal to the angular. So it's VA prime is just equal to this horizontal distance. Let's say that is, we'll find it out, but let's say, so this is GA and GB. So it's just equal to the distance GA times your angular velocity, right? So that's it's just omega r. That's what the velocity ends up being, because whenever you spin anything about that center, it's that omega r distance. The velocity about that center is just equal to the angular velocity times that horizontal distance from the center, right? And similarly over here, you'll see that VB prime. Now remember, this might seem a little abstract to you guys because we haven't really dug it in before, but it comes from the fact that, remember, when you're looking at r and theta polar coordinates, right? V is equal to theta dot r, right? That's the perpendicular V like that. So you can think of it in that way, right? So this is your transverse velocity, so to think of. Actually, you know what? Just think of it that way, because that makes total sense. So this is radians per second times 10 radians per second. Next, the trick is, all right, so what is the distance GA and GB going to be equal to, right? So that you can just find by your center of mass principles, right? You can say that the ratios of the distances remain the same, right? So that's what you can use to basically find where the location G is, right? So you can say that AG, and this is just coming from the fact that G is the center of mass, right? So AG over MV is going to equal VG over MA. This is equal to AG, and this is the known side, right? So we know that this is equal to AG plus GB divided by MB plus MA, like that, right? And we know that's just equal to AB divided by the total mass, so that's just 0.6 over 4.5, right? So doing this, you see that AG is equal to 1.5 times the distance 0.6 divided by the total mass, which is 4.5. So that's just 0.2. So AG, so this distance here is equal to 0.2. And that distance there is equal to 0.4, because we know the whole distance is equal to 0.6, right? So you know that this goes in there, this guy goes in there, right? So you end up with an initial kinetic energy. So your initial kinetic energy ends up being T naught is equal to, I'm just plugging in now. So we have 1/2 times 4.5. So that's the total mass of the system times the V naught velocity squared, right? So I'm just going to take the components and square them. So that is 1.2 squared plus 0.96 squared, like that, plus 1/2 times MA times VA prime, which is 0.2. The mass is 3, so 0.2 times 10 squared, like that, plus 1/2 times 1.5 times 0.4 times 10, and this thing is squared, right? So you do the math, you get that the initial kinetic energy is equal to 23.314 joules, right? And then you can get the final kinetic energy of the system when everything's broken up, you already know. So that's basically T naught is equal to T1. So you can say that 23.314, well, let's write out what this is going to be, right? So after the cord has broken, you're going to get the kinetic energy of A as 1/2 MA times VA squared, like that, plus 1/2 times the x component squared and the v component squared, right? So this is going to be VBX squared, like that, plus 1/2 MB VBY squared, like that. And this ends up being your third expression, right? So if we write it all out, you get 23.314 is equal to 1/2 over 3 times VA squared plus 1/2 over 1.5 times VBX squared plus 1/2 over 1 times 1.5 times VBY squared, right? So this becomes your third expression. So you basically have 3 expressions for 3 unknowns that you can solve, right? So I'm just going to know, you guys know how to use Mathematica, you're experts at all of this. So I'll just give you the final answer. We get that VB is equal to 3.6 I hat minus 2.24 J hat meters per second, and VA, well, remember you're writing it as a vector. VA is equal to 2.56 J hat meters per second. So these are your answers. All right, so this is for part A. For part B, so the trick there is that whenever it's asking you for this distance A from the y-axis to the path of A, immediately you can think of, all right, it has to do something with the moment or the angular momentum. And we know that we've learned a lot about angular momentum, right? So what we're going to do is we are going to conserve the angular momentum, right? And that will help us figure out what's happening. So what we're going to do is we are going to find out we're going to conserve angular momentum. And this is a little bit of a journey, so bear with me, right? So we're going to say that the angular momentum about the origin O initially is going to equal the angular momentum after everything's broken up. And this side, the right-hand side, is easy to do, right? Because the angular momentum for A, right, is just going to equal your unknown quantity A, right? And that distance is this distance here, right? So writing it as a vector, it's just A I hat, right? And B, you're already told it's going to be B J hat. You're already given that, right? So you can just directly put that in there. So you have AI, and remember, you're doing cross products now, right? So this gets crossed with your MAVA, right? So let's just write it out first. So it's MAVA. And remember, VA is in a vector, right? So this is the position. So this is your angular momentum for A, and then you get the angular momentum for B, which is B. B is in the also in the I hat direction, right? Because it's measured horizontally. So you have B in the I hat direction like that, and that is crossed with MV times VB, right? And this VA and VB, they're known to you now, right? So, and B is also given to you in the problem. B is given to be equal to 7.5. So here, you only have the one unknown A that you ultimately end up solving for. All right? Okay. So now we need to find out what the initial angular momentum is. So for the initial angular momentum, you'll remember from our notes that angular momentum about a point, right? So let's say that we're doing it initially. That is going to equal the position vector of your centroidal frame of reference, right? Crossed with the linear momentum of your centroid, which is given to you in the problem, plus whatever is the linear momentum of the centroid with, not linear momentum, sorry, angular momentum of the centroid with at initially, right? So this is a 0 and this is an O inside, right? So you're just trying to find out what the initial angular momentum for that is going to be. And if you go back, right, so now this is known, this is known. Now we need to figure what this guy out is, right? So this guy, if you go back, you can find out your centroidal. You remember now that you can just find out the angular momentum of the centroid about the centroid, right? That just makes life really easy. That's what we had found out and proven last time. So you'd said that this is, and now you can just also, you have the perpendicular components, right? So you can just, when you're taking the cross product to find them out, it just makes life really easy, right? So you can have that this distance there was 0.4, right? And this distance here is 0.2, right? And you know what these velocities are. You know the perpendicular direction like that. So this is equal to VB, which is, what did we said? It was 0.4 times 10, and this was 0.2 times 10 radians per second. Right. Next, you need to define, when you're doing cross products, you need to define a frame of reference, right? So the best one to do is just use your coordinate frame of reference like that, right? So let me draw it in black. So like that, in black, please, like that, and like that. So let's say that this is ER and this is E theta, right? And everything is going to come out to be a product of coming out of the plane, right? So for this frame of reference, the K hat is coming outside the thing, right? And similarly, even for your Y hat and X hat, even though this is, on the paper, K hat direction is the same, right? So whenever you're taking a cross product, you'll always get stuff in the K hat direction. So if you take a cross product in R and theta and take a cross product in Y and X, it comes out to be the same thing. So you can do that. That's totally okay. And that is, again, another lesson for you guys with cross product. All right. So now to find out this, I'm going to use this frame of reference. I'll have HG that point is just going to equal, so again, remember, moment of momentum, right? So it'll be, so this is G A, this is G B, like that. This vector there is just going to equal my whatever G A is crossed with the A prime plus whatever G B is crossed with VB prime. And then in this R and theta coordinate system, GA is just equal to 0.2, whoops, 0.2 ER, well, I'm getting hungry, ER, right, plus the A prime, which is not crossed with, A prime, which is 0.2 times 10, and this is in the E theta direction like that, right? Then you get the other one, which is plus GB. So GB is minus 0.4 ER, right? It's in the negative direction, but then B is also in the negative direction, right? So this is getting crossed with 0.4 times 10 minus E theta, right? So this becomes minus minus, so they just end up adding up, right? So ER crossed with E theta is equal to the K hat direction, right? So you can just write everything in terms of K hat. So, all right, I need a new page. So writing everything in the K hat direction and just looking at what you see that your HG originally is just equal to, and I'm just plugging everything in and saying that ER crossed with E theta is equal to K hat. So I just pulled the K hat out. So you get 0.2 meters times 3 kilograms times 0.2 meters times 10 radians per second, right? Plus the other one is 0.4 times 1.5 times 0.4 times 10 radians per second. And this whole thing is in the K hat direction. All right, so you can do the math to figure that out. So you get that that is equal to 3.6 kilogram meter squared per second K hat. And that's it, guys. You're done with everything that you need to do, right? Because in this expression, R and V naught are known. So you can write that H of O, respect to O, is equal to R bar, which is initially was, you're told that G is 2 meters above X, right? So it's just equal to 2 J hat like that. And that guy is getting crossed with your V bar vector, which is just 5.4 I hat plus 4.32 J hat plus 3. Now we got that this one, HG was just that. So that's where we're going to write 3.6 K hat like that. So J hat crossed with J hat is nothing. So you can just is itself. So you're left with J crossed with I, which is minus K. So you end up with the fact that you get minus 10.8 K hat plus 3.6 K hat like that. So that's equal to minus 7.2 kilogram meter squared per second K hat. All right, so this is your expression for HO. Plug it in over here and then equate it here, right? So if I do that, I see that so this is the equation, the HG expression, right? So I'm just gone back and equating it. So I see that it's just this equivalence, right? So it's that initial momentum is equal to final momentum, right? So you get minus 7.2 K hat is equal to AI hat crossed with 3 times 2.56 J hat, right? Plus 7.5 I hat crossed with, oops, this is not a multiplication, it's a cross product, crossed with 1.5 times the velocity. So this is basically your VA, and this is VB that I'm writing in here. So 3.6 I hat minus 2.24 J hat, like that, right? So I cross with J, so you're left with you'll get whatever 3 times. So basically one expression for one unknown. Everything is going to come out in terms of k hat, right? So I hat, you can get rid of this term. Cross with I hat is going to be 0, right? So you solve for A, and you see that A is equal to 2.34 meters, right? So that's your answer for A. So that's it, problem solved. All right, stop, reshare, figure everything, all the details are in there. It's a little bit over the top, but very, very comprehensive in vector form. And this is something which we're going to have to get extremely used to, because this is the kind of stuff we're going to be doing in rigid body. All right, rigid body motion. All right, thanks, guys. Hopefully this helps. Bye.